Hello and welcome to Umehluko Science Revision. My name is Dr. Douglas and I will be your host for today. This is the second lesson on the topic of acids and bases. And in this lesson, we will cover the following ideas. We will look at the concept of an acid-base reaction. There are various kinds of these, and we'll look at some examples. We'll look at a specific kind of acid-base reaction, which is called a titration, which allows us to work out some quantitative information about acid-base solutions. We'll also consider salt hydrolysis. We'll see that one of the products of an acid-base reaction is a salt, and we will look at the effect that a salt has on the solution of an acid-base reaction after the reaction is completed. Finally, we'll take a look at a very important component of these acid-base reactions, especially in a titration, and that is the concept of an indicator. All right, let's see where this leads us. There are numerous acid-base reactions, and you should be able to know generally what these reactions are, and then be able to apply these reactions to a specific system. So if we look here, see the first kind of reaction is basically an acid-base reaction that forms a salt and water. And this is known as a neutralization reaction. An example, let's say it's hydrochloric acid, HCl, plus a base, sodium hydroxide. And the products of this would be a salt. This just so happens that this is the main salt that we are aware of every day, table salt or sodium chloride, and the other product is water. So when you see this, an acid and a base, you know that the product is always some kind of salt. Doesn't have to be table salt, but the other product is going to be water. If we look, for example, another example of this sort of acid would be if we look at sulfuric acid, and we will react this with potassium hydroxide, then our product will be a salt. In this case, it'll be potassium sulfate and water. So what we have to do is, when we write these chemical equations, we have to balance them, make sure that the number of moles on each side is the same. In this case, to be able to balance this equation, we put a 2 in front of the KOH. That gives us 2 potassiums on the left, 2 potassiums on the right. We will have 2 oxygens on the left and 2 plus 2, in other words, 4 hydrogens on the left. So for this to balance, what we have to do is we have to go and add a 2 in front of the water. And now our reaction is balanced. Right, so that's the first kind of reaction. Acid and a base gives you salt and water. The second kind of reaction is that of an acid and what's called an active metal. And this will give you a salt and hydrogen. An example of this would be, let's say, HCl plus a metal like zinc. And this will form a salt, namely zinc chloride, and hydrogen gas will be produced. You notice that nowhere in this is there any oxygen. And so the product can't be water because there's no oxygen for the hydrogen to react with. So if we have something like this, then we will have a product of hydrogen gas instead of water. Another type of reaction is an acid and a metal hydroxide. So if we have HCl, chloric acid, and a metal hydroxide, let's say this is potassium hydroxide, will give us a salt, namely potassium chloride, and the product is going to be water. We notice here that there's oxygen in the hydroxide, and therefore water can be a product. Finally, if we look at an acid plus a metal carbonate, this gives us a slightly different product in that now carbon dioxide gas is released. So let's look at H2SO4 plus CaCO3, say it's sulfuric acid and calcium carbonate. This will give us the reaction of a salt. So the salt will be calcium sulfate. Carbon dioxide. From the carbonate, carbon dioxide will form. And then our final product is going to be water. So you should be able to look at any specific reaction, and you should be able to identify what kind of reaction is it. Is it an acid and a base? Is it an acid and an active metal? And so on. Or you should be able to take the general kind of reaction as given here and be able to predict the products of this reaction by knowing what the general products are going to be. Now we will look at a specific kind of reaction, and this is called a titration. Now, titration isn't really a reaction, it's more a method of determining quantitatively properties such as the concentration of an acid or a base in a solution. But it requires the first kind of reaction shown here, namely the neutralization reaction. So, as we've seen on the previous slide, a neutralization reaction is an acid and a base that reacts to form a salt plus water. We've mentioned this idea of a salt. What is a salt? A salt is a neutral ionic compound composed of cations and anions. So one part of the salt comes from the acid and the other part comes from the base. And this is one of the main products of a neutralization reaction, the other obviously being water. Now, for the importance of a titration, we need to understand the concept of an equivalence point. So if we add the acid and the base together to form a salt plus water, if we have an excess, let's say, of the base, it means that in our solution at the end, we will not only have a salt and water, but we will also have some base. Because if the base is in excess and the acid is limiting, in other words, there's not enough acid to react with all of the base, according to the formula, what is going to happen is that the pH of the final solution will be more on the basic side. And the same for if there's an excess of acid compared to the base. So what's important for us to understand is that for a equivalence point to be found, the acid or the base must not be in excess. And so what we can do to define the equivalence point is to say that it is when a stoichiometrically equivalent number of moles, in other words, according to your balanced equation, if HCl were to react with sodium hydroxide to form a salt plus water, what this means is that 1 mole of HCl must react with exactly 1 mole of NaOH to form 1 mole of NaCl and 1 mole of water. If we have one of these in excess, then we will not only have these products, but whichever substance is in excess will also be in the solution. And therefore, the equivalence point is that point where we've added exactly the correct number of moles of acid and base so that neither of them is in excess, and that our product specifically contains only the salt and water. So, what is a titration? Well, It's the method used to determine the concentration of a known substance using another standard solution. And this is why we defined the standard solution in the first place. Now, a titration reaction requires some specific equipment, and this is illustrated in the diagram here. So, first of all, this device here is called a burette. And this is where we put our standard solution in, which we are going to add to our unknown, and we are then going to measure the amount of the standard solution that it takes to exactly neutralize the unknown solution. The unknown solution sits here in the conical flask. This is our unknown. And it can be either an acid or a base. So it doesn't matter. You can add the acid to the base or the base to the acid, and the experiment will be equivalent. This is a burette holder. It is specially designed to keep the burette upright. The burette itself is marked off very accurately so that an accurate measurement of the amount of standard solution added to the unknown solution can be made. And this is what we measure. We measure the volume of the solution that we add. And knowing the concentration of the solution, we can calculate the number of moles that are in the standard solution. This here is a retort stand, which is used to hold up the burette, and this is called a pipette. The pipette allows us to take a very small amount of a substance very accurately, and what we do is we use the pipette, we take out the unknown substance, let's say 25 cubic centimeters or 25 milliliters of that, and we put that into the conical flask. This is our stock solution. In other words, our standard solution, and this is what we use then to work out the substance that goes in the burette. Right, so we'll go through the procedure in the next slide. So what we do is take a carefully measured volume of the solution with unknown concentration in the conical flask. So we use the pipette to put exactly the right amount of the unknown solution in the conical flask. Right? We then add an indicator to this. The indicator tells us when the equivalence point is reached. And an indicator is a substance that usually is one color in an acid and another color in a base. And when we find the point at which the color changes, we are able to find the equivalence point of the reaction. So the conical flask is placed on a white tile. We can see the tile at the bottom here. This white tile just makes the change in color easier to see. So the standard solution, which is of a known concentration, is put in the burette. So the known concentration is in this volumetric flask, and this goes into our burette. What we then do is we add the standard solution drop for drop into the conical flask, and we keep an eye out for the color change. So initially you'd add quite a bit and the color won't change. But when you get close to the equivalence point, one drop is enough to change the color completely from the color in acid to the color in base. And to find the equivalence point exactly, we want to find exactly to the drop which amount of solution has been added to the unknown to neutralize it. What we then do is we record the volume of the standard solution that has been added up to this point, and using this information, plus the balanced equation and various equations such as the number of moles as the mass divided by the molar mass, or the concentration is the number of moles divided by the volume, we can then calculate the concentration of the unknown solution. Let's do a worked example of a titration calculation. So if we look here, we see that 10 grams of solid sodium hydroxide is dissolved in 500 cubic centimeters of water. Using titration, it was found that 20 cubic centimeters of this solution was able to completely neutralize 10 cubic centimeters of a sulfuric acid solution. And our final answer is calculate the concentration of the sulfuric acid. So what we'll do is we'll start with the balanced equation for this reaction. What are our substances? We've got sodium hydroxide, and that sodium hydroxide reacts with sulfuric acid, which is H2SO4. And because this is an acid-base reaction, the products will be a salt and water. The salt in this case will be sodium sulfate and water. Remember that this equation must be balanced. So let's make sure that we have this balanced. And if we put a 2 in front of the sodium hydroxide and a 2 in front of the water, this will be the balanced equation. Now, let's find out how much sodium hydroxide we have in our solution. The first thing to see is that we've got 10 grams of sodium hydroxide. So the mass of NaOH is 10 grams. This was dissolved in 500 cubic centimeters of water, but we can't use cubic centimeters. We must convert to cubic decimeters. So our volume is going to be 500 divided by 1,000, which is equal to 0.5 cubic decimeters. We want to find the number of moles of sodium hydroxide. So the number of moles of sodium hydroxide is the mass divided by the molar mass, which is 10 divided by 23 plus 16 plus 1. And that gives us an answer of 0.25 moles of sodium hydroxide. Right. Now, we haven't used all the sodium hydroxide. The question tells us that 20 cubic centimeters of the solution was used. So we want to find out how many moles of sodium hydroxide were used to neutralize the reaction. So if our standard solution contained 0.25 moles of sodium hydroxide, what was the concentration of our standard solution? So the concentration is going to be the number of moles multiplied by the volume. So that is 0.25 moles of sodium hydroxide multiplied by the 0.5 cubic decimeters of our solution, and that is 0.125 mole per cubic decimeter. Now we've taken out 20 cubic centimeters of this. So 20 cubic centimeters is equal to 20 divided by 1,000. That's 0.02 cubic decimeters. What we want to know is the number of moles in the final amount of sodium hydroxide that was used to neutralize the sulfuric acid. So if we work with this example, we'll say that the number of moles will be equal to the concentration multiplied by the volume. Concentration we found to be 0.125, the volume 0.02, and that will give us an answer of 0.0025 moles. Right, so now we found the number of moles of sodium hydroxide that would have reacted with the sulfuric acid. What we now need to do is look at our mole ratio of our sodium hydroxide to our sulfuric acid. So if you look at the mole ratio of sodium hydroxide to the mole ratio of sulfuric acid, we see from the equation that it is 2 to 1. So therefore, if we had 0.0025 moles of sodium hydroxide, that would have reacted exactly with 0.00125 moles of sulfuric acid. So we know the number of moles of sulfuric acid that we've had. We know the amount of sulfuric acid, namely 10 cubic centimeters. So now we can calculate the concentration of the sulfuric acid. So if we do this, once again, we can't use 10 cubic centimeters. We must convert that to cubic decimeters. So this is going to be the volume in cubic decimeters of the sulfuric acid, and the concentration finally will be equal to the number of moles of sulfuric acid divided by the volume of the sulfuric acid, which is 0.00125 divided by 0.01, and that gives us an answer for the concentration of the sulfuric acid of 0.125. And the concentration unit is mole per cubic decimeter. So we've seen how we are able to take the information from a titration and we are able to calculate an exact concentration for our unknown substance. The next section we will look at is the example of salt hydrolysis. And this tells us that when the acid and a base reacts, the salt will give a certain character to the final solution. The salt will make the final solution acidic or basic or neutral. And this informs our choice of indicator. What this means is that at the end of our titration, our equivalence point does not have to be at neutral pH or a pH of 7. And this is what it looks like. If we see this table here, we see that if we react a strong acid with a strong base, the solution in the end with our salt will be neutral with an approximate pH of 7. If we add a weak acid and a strong base, that means that our final solution will be on the basic side, in other words, a pH greater than 7. On the other hand, if we have a strong acid and a weak base, this will make our final solution acidic and it will make a pH of less than 7. So remember that at this equivalence point, only salt and water are in the reaction as products because we have used up all our acid and our base at that point. Now, again, very importantly, strong and strong gives us neutral. Strong base gives us a basic pH, and a strong acid gives us an acidic pH of the final solution. Indicators are very important for us to be able to determine the equivalence point as they change color when the pH goes from acidic to basic. Now, depending on the kind of titration, different indicators may be used, and an example is shown in this table here. So if we have a strong acid and a strong base, we'd like to use the indicator bromothymol blue. This gives us a very definite color change. In the acid, bromothymol blue is yellow. In a base, bromothymol blue is blue. And at the equivalence point, bromothiamyl blue is green. And so when we have a strong acid and a strong base, where the equivalence point is near the neutral pH, we will use the indicator of bromothiamyl blue. In this example here, this shows us the colors. There's the color in acid, there's the color in base. And if you have equal amounts of yellow and blue, that makes green, which tells us that at the equivalence point, bromothiamyl blue will be green. Similarly, we can use the indicator phenolphthalein when we have a weak acid and a strong base. In an acid, phenolphthalein is colorless. In a base, phenolphthalein is pink. And at the equivalence point, this will be a very light pink color. So the color change will be from colorless to light pink. And this is shown in this diagram here, with the endpoint being in the light pink range. Finally, if we have a strong acid and a weak base, we expect that the final pH will be less than 7. So we need an indicator that changes color at a pH of less than 7. And an example of this kind of indicator is bromocresol green. Bromocresol green is yellow in an acid, as seen here. It is blue in a base, as seen here, and therefore, at its equivalence point, it will be green, as shown here. And the pH range for this is between 3.8 and 5.4. So knowing which indicator to use depending on the kind of reaction we have is very important. Thank you very much.